So in the previous class, I taught you about the PD controller, and I told you that it tunes transient response and stabilize an unstable system. Specifically, if you remember, D was tuning the natural frequency of the system. I'm sorry, P. And the D also tuning, adding damping to the system, zeta kind of, and stabilizing the system. So can you hear the screen? Yes? So let's go today to the MATLAB, and I design a real PD controller for the example that I started from the first class of the control class, that is particle mass. And in the previous class, we had, if you apply a control torque here, tau or U, I said that from the first class, theta of S, open loop transfer function over U, by assuming that the mass of the particle is 1. Oh my god. This means that M is 1 kilogram and the length of the pendulum is 1 meter. Okay, is 1 over S square plus omega n square. And you know that the omega n of the pendulum from the first class is G over L, and gonna be 9.81. So omega n square is 9.81. Sorry. And if you remember that we had this, I said that I want to keep the desired the pendulum at the desired angle of pi over 4 or 45 degrees. So I need a PD controller here. So we need a controller. Here we go. This is the error signal, and this goes to this U control command that I'm going to do in MATLAB today. To the plant is pendulum here. See, theta over U, 1 over S square plus omega n square, open loop transfer function. This is your G, and this is the controller, remember? And this gives the real theta. Here we go. Theta over U is 1 over the square. And through the ideal sensor, this is being feedback to be compared with the desirable angle that you want to keep, and this gives you error signal. So the error signal, because I'm going to do hopefully today in MATLAB also, is theta d minus real theta. Obviously, here is plus, here is minus. So in the previous class, I introduced you that the KP P controller plus KDS. And if you remember, we ended up by simplifying this block diagram. Theta D, desired angle, and plus minus. Now you are multiplying two blocks, you get your new G, remember from the previous class? You're going to be KP plus KDS divided by S square plus omega n square. This is going to be real angle that is being measured and be compared to the desired angle. So the closed loop transfer function, output over input, theta over theta d, this is open loop transfer function. Was, if you remember from previous class, was KP plus KDS S square. KDS comes down like this. Now you're adding missing S from here, plus Kp plus omega n square. Oh my god. Plus omega n square. So this is your closed transfer function by adding the controller. And I told you, based on whatever I taught you in this class, you can compare this with typical the second order system I taught. S square plus 2 zeta omega ns plus omega n square. You see that the D controller adds damper to the system. It's good. Obviously associated natural frequency. And P controller, see, it is tuning, adding to the natural frequency as we defined here. Okay. So the system pendulum, by assuming that there is no friction here from the first class, had a pair of pure poles. So P1 and 2 was plus minus I omega n. And if you remember this is imaginary and real. So it had this. And I taught you from the first or second class, if the pair of poles of the system is on the imaginary poles, means the system gonna oscillate forever. This is not good because we want to keep it at the 45 degree. Clear? Yes. Everybody? No. Yes. Yes. Good. So, but now by adding the D controller, meaning damping, so we are promising to the system based on the second order system analysis that I did in this class. You're gonna say, okay, you know what? After this, I'm gonna have the underdamped system, critically damped system, or overdamped system. Means I'm gonna have a pair of complex conjugate poles, or I'm gonna have a repeated real poles, or I'm gonna have distinct real poles, not imaginary poles. So by adding controller as a control engineer, you are saying, you know what? I'm gonna move this to here, or I'm gonna have these poles, repeated poles, or I'm gonna have repeated poles like this, distinct poles. So you are fixing the system. I mean that you are moving to the left hand side. Okay, so now I'm your boss. I'm saying Mike, Mary, Jonathan, I don't know, Elizabeth, go and design a controller for me that your pendulum. And guys, you may ask me that, Payman, are you out of your mind? Why you stick to the pendulum? Let's assume the Mars rover. You have seen that? Mars rover? Okay. Has a manipulator at the end to pick up the object from the Mars. Now let us say in the future we're gonna have a Mars rover that has 1 degree of freedom. This can be a robotic arm, guys, like this. Okay, this is a robot. 1 degree of freedom robot can take the object from the ground and put it back to here, to the rover. So that's why the pendulum is super important example of the dynamical system in field of dynamics, control, and robotics. Because it reveals nonlinearity, sine of theta, then it reveals too many things if you go to the grad school nonlinear dynamics. And in robotics, this is the most trivial robotic system in the universe, 1 degree of freedom. As long as it is can be modeled, as I told you, as model of your leg when you walk. As long as you can say, if you keep the joints of your hand fixed, it can be your hand when you walk. That's why the pendulum is very important problem. Okay? I'm saying, okay, John, Elizabeth, go and design for me that not only remove this oscillatory motion of the pendulum, but keep it as 45 degree, but I want to have underdamped response. How, as I stated in the from previous class, I say the maximum overshoot for the underdamped behavior, transit behavior, is 25%, and peak time be 0.2 seconds. Means, I'm going to do in MATLAB today together, okay? So, means, originally the system was this. That sucks. Now I'm telling you, design a controller for me, PD controller, that does this for me. Here we go. I'm transferring this ridiculous response to this. I'm saying that this is, I'm your boss, I'm paying you because you're my engineer. TP must be 0.2 seconds. And this peak must be 25%. Design a controller for me. When I'm saying design controller, I mean that go and determine KP and KD. Okay, let's do that. I started from previous class, but today more specific. So 25% means, remember that in the second order system I taught you MP is E minus zeta pi 1 minus zeta square. So 25% is 0.25, gonna be E minus zeta pi 1 minus zeta square. What I'm gonna do, I'm gonna apply the Neperian logarithm, national logarithm. So if you do that, you're gonna have ln 0.25, and here you're gonna have minus zeta pi 1 minus zeta square. Okay, this is the equation to find zeta. How to do that? You know our lovely MATLAB. I'm gonna go step by step today to design PD controller for you. Okay? MATLAB. So what is your unknown in this system? Zeta. We want to find it. I'm saying zeta. What happened? I'm saying okay. I'm saying your variable to find zeta is x. Okay. Until MATLAB comes up, it's coming. I'm recording. Yeah. Okay. So what I'm gonna do, I'm gonna file in this. I'm gonna say zeta is a double, because remember, solve, which solve? This equation right here. Log 0.25 plus zeta x pi 1 minus x square. So before that, because I have to define this, sims x. So log of 0.25 plus divided by pi multiplied by x, means that is zeta you want to find, sqrt of 1 minus x square. This is for this, this is for this, and this is for this, and this is for this. Everybody clear? Yes? This is solve that we always doing this, right? I'm only changing to the number by double command. Understand everyone? I'm saying ME530 controller PD. I'm going to share with you. Okay, let me double check everything. So yeah, because we are going this to the other side, that's right. So it's going to be plus. Equation is this. So see, it's plus pi x. So let me run it, because I told you step by step. If I do that, you see it gives you damping ratio of 0.4. So it means that your system is under damped because zeta is smaller than 1. Understand? Yes? Remember, everybody?
Yes.
It's a good proof. Now, let's back to, so zeta is, we find zeta is 0.4037. We found it from MATLAB. Here we go. Here we go. This value. So, okay. Now, let's just stick to this. As I taught you, TP, peak point, is pi over omega d. Your boss says, I want to have the peak point of 0.2 seconds. Meaning that omega d is pi over 0.2. We know, and I taught you, that the damped natural frequency is omega n 1 minus zeta square is pi over 0.2. So from here you can find the natural frequency is pi over 0.2 multiplied by 1 minus zeta square. Let us do that. And let me name this new natural frequency. Remember from previous class? Name this. Mr. Gordon? Yeah. Name this new natural frequency, omega n1. That's right. Because this is, you're getting this based on the controller. So I'm gonna now do again in MATLAB. Okay, so after having this, I'm saying omega new n1 is what was the number? Pi divided by okay, and we got zeta squared from the above line, that's right? Yeah, we got this from here. And that's it. Now let us see what's the natural frequency. Natural frequency is 17.1693. Means by adding the natural frequency, guys, I want to make a point. Everything has a reason. 17.1.6. So natural frequency, tuned natural frequency, tuned is 17 point, how much? 16 radian per second. Guys, look at here. The original natural frequency of the system was how much? This value. And was 3 like that. By adding the PD controller, P part, increase natural frequency of the system to 17.16. Do you see my point? When I say the P controller tunes the natural frequency, I mean this. Understand, everyone? Yes? Okay.
Yes.
So why we are calculating zeta and omega n? Where is that? Here we go. Because KD is 2 zeta omega n. Here we go. So your D derivative gain is 2 zeta omega n. 2 multiplied by 0.407 multiplied by 17.16. Simple like that. So let's go to the MATLAB. I'm going very slow to make sure that you fully understand the PID controller, okay? So your KD controller gain is 2 zeta omega n nu. If I run this, your KD is 13.8629. The gain of D controller. Bingo. And now let's go back to the P controller. Okay. Your new natural frequency, okay, is Kp plus omega n squared. Get here. So omega n1 squared is Kp plus omega n squared. Here. See? This is your new natural frequency. Okay? So from here you get Kp is new natural frequency squared minus old natural frequency squared. Everyone agree? Are you following me? Yes? Yes, guys? Okay, so P controller gain is where are you? Okay, so PKP is omega. Oh my god. Omega n1 squared, but we didn't define the old natural frequency. For the pendulum, old natural frequency is omega old is SQRT of, I'm writing like this to teach you generally, G over L, remember, for the pendulum. G is 9.81 like as coding, L is 1, okay? So omega old is SQRT of G old. So it's going to minus omega old square. So let us run it. Let me, because I'm going to share with you. Let me, so your Kp is 284.97. Okay, good. Now we design the controller. So what I'm going to do, I'm going to plot it. What? I'm going to give the step response. Okay, step response. Okay. And Kp plus Kds divided by this. See what I'm saying? So your num is this second order system, guys. So your num, as I taught you, is 0 KPS, KDS, KD, and plus KP. Here we go. Your then is 1 KD, that's right, and KP plus what? Look at here, exactly like this. Kp plus omega n squared. See, omega n squared. Old omega n plus old omega n squared. Here we go. Now and then. So then I'm gonna say figure 1, step now and then. Greet. Bear with me, okay? So if I do this, guys, okay, let me debug it first. Oh, P is lowercase, lowercase. Here we go. So you see that we said that peak time is 0.2, but it's very close to that, not exactly that, 0.15. And almost you have 25% overshoot. Okay, the system was like this, oscillatory. Let me change this, guys. Time 1, 2, 3, 2, 5. And here is time. And okay, and I'm gonna say hold on. Okay, I'm gonna plot versus the original row without controller. Num is 0, 0, 1. This is controlled. This is uncontrolled. Okay, uncontrolled. Okay. And its then one was 1, 0, and omega old square. Remember? Okay. So, what are these? So I'm gonna say, hold on, step, now 1, then 1. Here we go. I'm gonna say this is, what's happening? Oh, 1 must be here. And always put this clear all, close all. There we go. With this oscillator's response to stable and with almost 0.2 peak time and 25% what? Overshoot. 25, almost 25% overshoot. Here is almost 25%. And the peak time is that. Okay? Understand everyone? Yes? Yes, everyone? Okay, so you see that now design your first controller. Now, guys, I asked you a question. I told you that I want to keep that angle to how many? Pi over 4. Pi over 4. But pi over 4 means how much? Let me give it. Pi over 4 is 0.78. 0.78. But it gives how much? Almost 0.98. It goes there, but it's stable, but it's different angle. So what I have to do to keep it as 0.78 pi over 4? Can it brainstorm for this for me? Look at here, guys. Look at here. Give me some ideas. Your theta d, look at here. This theta d is pi over 4. I want to keep it at pi over 4. How about, guys, because theta d, look at here, guys, When I say pi over 4, it means pi over 4 step function, that's right? Yes? Yes? How about
Yes.
I transfer pi over 4 to the numerator here, pi over 4. Can I do that? And here only is a step function as we do. Right? Can I do that?
Yeah. You can.
Yeah, so let's try if it works. So what we're gonna do, I'm gonna say, you know what? I'm gonna say multiplied by pi over 4. Ooh, here we go. See? Let's see what's happening. Yeah, it worked, man. It's 7.8. You see that? What I'm saying? Okay. Now your pendulum, based on the controller that you designed, going to 45 degree, okay, or pi over 4, which is 0.78. This is the radian, that's right. This is radian, okay. And with the overshoot of almost 25 and the peak time of almost 0.2, almost. See what I'm saying? Yes. Now, if you want to have a better vision, let me say I multiplied this by 180 divided by pi. Let's see what happens. What happened? See the numbers. 45 degree. Okay, I just changed it to degree by multiplying by 180 divided by pi. Right? This means change radian to degree. Now if I say, okay, push that to 60 degree for me, pi over 3. Here we go. Almost 60. Almost 60. You have a little error signal here. A little. I'm going to talk about this later. Okay? Almost 60. Let's say push to 30 degree for me. Here we go. Almost 30. Not exactly. See what I'm saying? Okay. Has a little error signal. So that's it. Here we go. Okay. This is one. Now you learn how this is one way of coding, but this is not the most favorite one. Okay? Before going to the I integrator, I'm going to teach everything in MATLAB. See what I'm saying? Now let us say to step impulse delayed. Yeah. Let me go to the Simulink. Good. Whoa, come on. Okay. So I'm gonna click thumbs up. Okay, good. I'm gonna copy this, make a new one. Thank you. And first of all, I'm gonna keep it as 45 degrees, that's right. Final value gonna be pi over 4. That's right. 45 degrees. Great. Then I'm gonna remove this. We don't need that. And now open loop transfer function of the system was 1 over 10 and 9.81, the old natural frequency of the system. Now what I'm going to do, I'm going to go to the library and I'm going to type here PID. Here we go. PID controller. I'm just dragging, putting here. Then I'm gonna embed it here like that. Then I'm gonna double click on that. Okay. Why? See, P gain, I gain, derivative gain. I didn't teach you I gain yet here, but I can put what is that? KP and KD gain from the code that we calculated. Okay. So KP, so KD was this. I'm just copying from here. I'm putting here KD. And your KP was this. Here we go. And apply. Okay. Then I'm gonna back here. And remember, this is your open loop transfer function. 1 over s squared omega n squared. See? I just did here like this. 1 over s squared plus omega n squared. Okay? And this is your PD controller. Where's that? Okay. P gain, D gain. I put I still 0 because I didn't teach you yet. PID. Okay? So, and then I'm gonna say Simulink PD controller. Let me just being saved. Okay. Now I'm running that. I'm gonna put in 5 seconds. Okay. And I'm comparing the output with the desirable input. Here we go. Oop. Do you want to do it or not? Here we go. The blue is desirable input and output almost very slightly error signal is here. But we made unstable system like this, remember? And we made it stable with almost 0.2 peak time with almost 25% overshoot. Good. But we have a slight error signal here. Very slight. Okay. I'm going to talk about this later. So that's it. So even if that you plot the error signal here and run this, See, starting from huge value, almost going to 0, not exactly 0. Almost. Now guys, before going detail into I need another coding style that you're gonna do when you graduate. Okay? That is OD style of the PID controller. But before that, let me just play with the PID controller. We did P, we did D derivative. Let me put the number of 1 or 2 for the I controller gain. I. Okay, KI. Here we go. Let's see what happens, guys, just for playing with that. Nothing happened too much. Okay, let us increase that to 50. So what's happening, guys? What's happening? Huh? What's happening? Yes. Yes. So let me increase it to, I don't know, 200. Bingo. So now you teach me, what's the function of the I controller? Or, yes, or to remove error signal, right? So before going to the math of that, I just by playing some numbers, you taught me that the I controller function is to fix steady state response. PD controller was tuning transient response, but the I controller is fixing steady state response, means removing what? Removing the error signal. If you now look at the error signal, it almost goes to 0. See, the equation goes to 0. Error signal. You understand what I'm talking about? Yes, but I didn't teach you math yet. I have to teach it. So now this is another. Let me close it. Let's back to our lovely PD controller. Guys, let me first go back to our problem. Okay. Here we go. So, remember the first class. The original differential equation was this. G over L is equal to tau, or U. Remember first class for the pendulum? That we said this is the natural frequency square. Omega n square is equal to U. This is controller that we designed today. But remember, when you were solving without any controller, I taught you the ODE coding in MATLAB. So you have dm1 equals to m2 if you transfer this to ODE as you had in the midterm. So dm2, which is theta double dot, was here is U controller minus what? Because here you have theta, that's right. Here you have theta. That's right. Minus omega n square m1. Right? Yes? Remember, the state variables m1 was theta and m2 was theta dot. the first class of this course. So dm1 time derivative, dm1 is theta dot is m2, dm2 is theta double dot is u minus omega n square m1. Yes or no? Yes?
Yes.
So, yeah, must. So here we go. Now I'm gonna back to MATLAB, because when you graduate, you're gonna see huge systems, okay? And they are nonlinear. You linearized and designed PID controller, but maybe you wanna run controller on nonlinear version of it. I'm gonna teach you today and the next class, okay? Bear with me. Oh, where is the MATLAB? Oh my God. Oh, okay. Okay. So I'm gonna do that. Function dm equals to controller PD T and M. I'm gonna save it here as it is. Okay. And then dm, we have two state variables is zeros, 2 and 1. And I define again gravity as 9.8 meter per second squared. L is 1. We don't need that, but the mass of the system, mass of the pendulum is 1, obviously. Okay, whatever. So, and oh, dm. Okay, and so now dm1, remember, is m2, and dm2 is u controller that we designed minus, and the natural frequency of the system omega n is sqrt of g over l. Okay, omega n square multiplied by m1. You see differential equation. What we only added is the controller. Is controller u. Now I'm defining u. U is kp as we designed. Oops, sorry. P controller plus kd. Okay. Now bear with me, because I have to teach you. Okay. Actually, I taught you. I'm just reminding you guys. Let me delete all of these. Okay, guys. What's the transfer function of the controller? Look at the previous class I taught you. Transfer function of the controller is u, remember from the previous class, is u over what? E. Yes or no? Yes or no?
Yes.
Okay. Equals to kp plus kds. Yes or no? Huh? So
Yes.
on the other hand, is u is kp e plus kd es. Yes or no? Okay. Now I'm gonna back to the time, because it's ODE, Laplace inverse. So u of t is kp error signal plus kd. What's the es? I told you a million times. When you see s, means what was the Laplace? What was the Laplace of that? Which? Yes, it's gonna be e dot. Here we go. Understand, everyone? So, but we defined E. Here we go. E is desirable angle minus real angle. Okay, good. Desirable angle is pi over 4, for God's sake. Real angle based on the state variable is what? M1. Here we go. Got here? Here we go. You see, step by step. So E dot gonna be minus M dot 1. What is M dot 1 based on the state variable? What is M dot 1? M2 minus M2. Here we go. Let me go for it. You see, it's interesting, right? So, because when your system becomes complex, it's better that you code it. So it's gonna be in E and in DE, means D dot. I'm defining this, right? So E is, let me say, theta desired, always coded, don't write, minus real theta, which was M1. Here we go. What is theta desired? You can change it after coding. It's pi over 4, 45 degrees. So DE that you defined here below for KD was how much? Minus M2. Here we go. We developed together, right? Yes, everybody? Do you have any question? Stop me. We define E as desired is power 4, theta is M1. Having time derivative is minus M dot 1 based on the state variable. M dot 1 is M2. So it's minus M2. So now you have U, PD controller. I'm just using here PD controller. This is error signal. This is derivative of error signal. Signal. Okay, and this is desired angle. So now you define U. But what is KP and KD? Because you have to define it. We already calculated that, that's right. Okay, KP and KD. I have to rerun it to copy and paste here. Your KD is this. Here we go. Oof. Your KD is this. Oh, 13. Your KP is this. Here we go. Now you have the PD controller in the hand. Everybody agree? Yes? You see that this orange line means we don't need that. So comment in your code if you don't need that. Okay? Now I'm gonna go for it, solve it. I'm gonna say clear all, CLC, close all. I'm gonna say time is between 0.01 to 5 seconds. I'm gonna say this and theta time and the theta angle equal to ODE 45 at what? Controller PD, this file, and time and initial condition. You have two state variables, 0 and 0. Initial position, initial velocity, angular velocity. Then I'm gonna say figure 1. I say plot total time t and the angle of that, bear with me, all the rows and columns, but in degree for me, please. And blue and grid X label. Bear with me, okay? Because I have to teach too many things here. Label theta in degree. I say PD coding. Clear all CLC. Close all. First, let me debug it. Here we go. Almost 45 degrees. Remember that eye control I didn't teach you yet. With 0.2 as the settling point and this. See? Why? What this shows that for me? Oh, time. Okay, so we have it. Not only you can have that, coding gives you ability to plot the velocity of the pendulum at the same time. That's why I always tell you go to the coding. Simulating is for the kids. Okay, here we go. But you have to remove this. See? Here we go. See, obviously it starts based on the control input, comes down, and at 45 degrees stops. So velocity is 0 here. Everybody understand? Yes? Yes? So let me first, why this? Oh, theta must be like this. And this is d theta. And this is radian per second. Radian per second. I'm not done. I have too many things in this coding. Okay, here we go. D theta, radian per second, time, theta, degree, time. You made a margin stable system by PD controller like this. There is one extra bracket here. Okay. So I'm not done yet, guys. You're gonna tell me why. Because I want to plot the error signal in the code. What I'm gonna do, for God's sake, I'm gonna put a counter here, con 0. This is how we code professionals. Then I'm gonna say counter equals to counter plus 1. In each time that it's going this code, this counter is gonna be like that. And I'm say global counter. And I'm gonna say here global counter in the code. See, now it's recognizing counter. Let me put the space. Okay, so this is your E, that's right. I'm gonna say E of plotting con equal to E. Every time that this ODE calls this is gonna put E as a vector inside here, guys. Do you want to try it? Let me show you. Pause. Pause. Look at here, guys. Look at here. Oh, why are you putting 0? Oh, what happened for the global here? Global count. Okay. Oh. Okay, sorry. Hopefully this time works. Oh, what's wrong with it? First, let me fix it. Okay, so global con, the problem was that I didn't global EP here, okay? So this works. This is counter. Now you see that if I run this, oh, not this, this, if I run this, see, it's gonna put in the vector. See, it's decreasing. See, it's changing. Put in the vector. So if I do that, and I'm removing pause, okay, then you can say figure 3. I want to see the error signal because you already defined EP as the global things. It's gonna be error signal E. Hopefully it plots. Oh, I have to define it here also. Sorry. EP. Oh, okay. Understand. So you know what I'm gonna do? I'm gonna do the same for here. Time of plotting con is t. Time. This time. So I'm gonna put as TP as TP. Now instead of that, I'm using this TP. Here we go. And it's gonna plot for me. Here we go. E, as you saw in the Simulink, error signal. But I now, bear with me because I have to finish this. It's very fast. Now I'm gonna see which control input you of plotting made that happen to me. UPCon is U. Okay, so you're gonna UP here, and you're gonna define UP here. It's recording, right? Yeah. It's gonna be UP here, control input. Here we go. And figure 4. And it's gonna be UP. And obviously your UP is torque, that's right, remember? It's tau, Newton meter, obviously, no doubt. Because this is pendulum. And this is the control command that you designed. And this is the torque, 200 Newton meter comes down to this and this. This is control torque that you designed. We don't have still I here, see? But by having I, this gonna probably go to a very low. And this is how you control everything. And if you zoom this in, see that, let's look at here. Do you see the control effort? It's not smooth. Do you see that? Yes, everybody? Yes? Okay. I'm not done with the code yet. It continues before going to the I. Okay? So, but you can have this code as a graduation, and if you have, I don't know, 10th order system, you have 20 state variables, you design controller, put it here, bing, done. Okay? Everybody? Okay. So see you next class, guys. Bye. Thank you.